The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Well, hey there. Welcome to Skytour Livestream. It is I, Mark D'Antonio. It's so nice to be here with you guys tonight. I literally just got back from the observatory out in the desert tonight. I'm all the way back across the United States, 2,500 miles away, back here in Connecticut. And I figured I would just bring you a little bit of an update, show you what's going on. I've implemented a new function within our processing. If you remember, sometimes we would take photos and you'd see a blur, blurriness. Well, it's kind of windy out there tonight. And so if you notice, I've got a perfect stack of so far 8 frames, right? And that perfect stack of 8 frames is because I've rejected 14 frames that fall outside of our blurriness scale. So I've implemented this scale. And if I mess with it, you can see that some of these numbers are red and some of these are green. We had 8 good frames, and then we had some wind kick up, and as you can see, the next frames that come in are red, so that we have some wind out there. However, it doesn't affect our image, if you notice. So this is how we're going to be able to make sure we never have bad frames. I could, now if you notice, the numbers are 8.46, 8.02. I could squeeze this number up just a little bit, maybe to say 8.16, and maybe some of these would squeak through if they get down lower. But I haven't even focused yet. I just wanted to run this and see. You'll notice some satellites have gone through. These are spent rocket bodies. You can tell because you'll see that they're bright, then they get dim and darken out, then bright, dim and darken out. These are tumbling rocket bodies that are up in orbit. So that's kind of cool. And that tumbling process is something that, we basically just have to accept, right? Until we can clear these guys out of orbit, which could happen at some point. I know that NASA wants to actually clear them out. I know they've got some plans to do so. But this, by the way, is the Helix Nebula. I want to say hello to you guys. I want to say hi to Tim F., who was first. Yeah, hi, Tim. And we have Alice Pooper. And Asher is with us. Hey, Asher. Papa Tom, good to see you. Jessica S., nice to see you as well. And I want to say hello to Cindy Murphy and Curtis Horn. How you doing? So, so now what we're going to do, like I said, is we're just going to look at a couple things here. As I said, I just got back from Arizona tonight and flew cross country. And I figured, why not? Why not just bring you a little bit of a stream tonight and see what we can do? You'll notice one of the screens, now it's up at 9. If we go here and look, we'll see that we caught one. One came in that was reasonable. All these were not. These guys were not reasonable. And we look back and we'll see that we have several green ones that were reasonable. And we see that I have a pretty tough setting on here right now. But it guarantees that whatever comes in is going to make a perfect stack. So this way we as we take these images and stack them on top, if these images have some unfocused areas, they get rejected. So we're only stacking the best frames. And so far that gives us 9 on a windy night. It's fun to do this on a windy night because you can actually watch it create a perfect shot even with the wind blowing out there. That's pretty cool. Okay, so this is the Helix Nebula, a planetary nebula. That star, that remnant in the middle here, that is actually a white dwarf. It's the size of our Earth. And it is 45,000 Kelvin. It's actually quite hot. As I said, I didn't even focus this yet. I just wanted to do this test. So I will focus it now. So we'll go back to our histogram. And we'll get out of the stack. I'm not going to save it because I'm not planning on saving this at the moment. Let's go here. All right, so. All right, goodness, that's good. Now we go to our quick picks. Go to 1 second shots here. And then maximize. You're going to notice something else now that's different. I've added another feature. You'll notice it doesn't look green anymore, and you can see the Helix Nebula there in true color. What I've done is I've added automatic dark frame compensation. Something I had to be there to do. I couldn't do it otherwise. So we have it, we have it now implemented. So this is all good. And along with the other feature of adding in the rejection for unfocused frames or for frames that are out of round by a certain amount. The image has to be a certain amount of size. That gives us now a really good base from which we can get some good shots. Okay, so I'm going to defocus this, and then I'm going to refocus. We've also upgraded our internet at my end here, but it's being installed now, so it's not perfectly ready. But we've gone to a gigabit internet so that we can get upstream and downstream speeds that are exceptionally high. And when you're doing streaming, you need upstream. Now, out at the observatory, we don't have a very fast upstream, because we're using Starlink out there, and our Starlink out there is actually just a little bit on the low side. It's much higher than what we had, but it's a little bit on the low side because of the fact that we're in a low bandwidth location. But that's going to change. We have some better internet capability coming to us soon. Hello there, Michael Galea and Francis Palmer. How are you? Excellent. Okay, we're just getting our focus here, and then we're gonna come back and check out something else now. Okay, you see our curve now is pretty clear now. Excuse me, you're going to see a line appear right about here. That's my guess. All right. We should see it right there. There it is. Okay. So now, I will select best focus. And it will focus. Those markers, Asher, are focusing sample stars, because we just did a critical focus. And when I get rid of this focusing segment here, these dialogues, you'll see that they go away. So there's the Helix Nebula now. And just for a test, we can try a 25-second shot. Actually, we don't need to go 25 seconds. We'll go 20. And you'll notice I'm putting in 20,000. That's because this is a millisecond number. So 20,000 milliseconds is 20 seconds. All right. So now we drop down and go into our live stack, and you'll see the previous shot. Okay, and the stars are just a little out of focus. However, in the next one, you'll see that they are not. Let's go in here. And let's see what we get. Okay. So our first image comes in nicely. All right. And so it has a little noise in it, as you can see. Let's see what this one does. And that one's in the green as well. And notice how much improvement in just 2 shots. Oh, Papa Tom, I'm sorry you don't have good Wi-Fi. Curtis Horn says, Mark, I sent you an email. Gave a talk on Tim Ventura's YouTube channel. Let me know what you think when you get a chance to see it. I will indeed. Thank you, Curtis. I will check it out. Notice we have all green here. We're actually getting some green shots here. Ideally, if they're in the 6s, we're going to get some gorgeous stars. And as you can see, that white dwarf in there is quite sharp and round. notice there's also this outer halo of material that was expelled by the star. It's glowing red, so it could be ionized hydrogen, but this is blue because it's one of the hottest things there is. And if we can zoom in a little bit, all right, you'll see that star, that blue star, is really exceedingly blue compared to the surrounding stars. Let me just try to show you a little better without some of the noise. Let's remove some of the noise. So now you look and you see that? That's really blue, and these stars are not. The blue, remember, blue in the universe, O stars are hottest, but they're also the bluest. So this little white dwarf, even though it's a stellar core remnant, it's actually something that's quite hot, right? And that remnant heat left over could take billions and billions of years to cool off. So let me see if I've got any enhancements on here. I do not. We're not going to use any. And using them sometimes will increase noise like that. I do not want increased noise. I want reduced noise. So there. So we're going to leave it off. And the more frames that come in, the better it will look. And if you're wondering where this is, the Helix Nebula is actually in the constellation of Aquarius. Aquarius is here, right? And Aquarius is the water bearer, the water carrier. Saturn is also in Aquarius, and we'll take a peek at that as well. It's literally right near the helix tonight. But let's go down and center up on this, and let's also synchronize on this. There we go. So as you see, this looks really nice. We have 12 frames. None have been ignored. So if we come over to our full width half maximum string, we can see that all of our frames have been coming in just fine. In fact, these are exceedingly low and beautiful numbers. I can actually probably drop this down. I'm going to bring it back down to what I had it to before, which is around 7.5. And that will guarantee that we have perfectly round stars now. We'll never have to worry about a bad stack anymore. Because if the stars aren't good, it just selects the best stars, selects the best stack values, and ignores the stacks that would otherwise make these stars kind of elongated. You've seen that before when we've done this. Well, we'll never have elongated stars again, because this is now a permanent setting that we're going to be using. So the temperature out there, the first day I got there was 91. Second day was 98. And then on the remaining days, it was a little cooler at around 87 to 90. Really nice. And then I came back to Connecticut, and the temperature was frigid 36. It's like, was not ready for that. Look at that. Isn't that gorgeous? You can see some really interesting details now in the helix that we couldn't see with the other camera. New stuff available to us. Hey there, Sam S. Sam S just joined us. Francis Palmer says, just been out looking at Betelgeuse because it's 4:12 here in the UK. The sky is nice and clear. It's a bit brighter than it has been in previous weeks for sure. Yeah, Betelgeuse is a variable star, so there's no doubt that you will catch it at different brightnesses. No doubt. Let's see if we've lost any frames. Let's go over here. I am waiting for Starlink. Alrighty. Alright, one moment. I'm going to bring it back. Alright, let's see now. Just a second. Okay. We're gonna just, yeah, I know. Like that? Me either. Okay, there we go. Alright, and then this. Pull that in. And pull this up. And we should be good. Okay, 1 second here. Let's get this back up, get this window up here. There we go. Alright, so that's looking good. We've got no rejected frames so far. We have 23 frames stacked. Not bad, so we can save it right here. That's the Helix. That's going up to our amazing server, which you can get to by going here, skytourlive.org. And you can hang out there and go get these images. They're all free to take down. The image that you see right here on the screen will be made available to you on that server without any reason. Yeah, it is a wild temperature difference between Arizona and here, Jessica. She says, what a temperature difference. Yeah, and I still had my little black widow spider at the bottom of the door going into the observatory. But hey, as long as you don't mess with them, they won't mess with you. They don't leave their webs, so that's all good. So this is a very big planetary nebula. You can see this beautiful, let's see if we can zoom in. You can see the detail in here. Look at this detail. Look at that. It's incredible. There's a lot of really interesting detail in here. Let me do an enhancement just to see here. Yeah, let me drop down. Let's go to that. Look at that. Look at these radial lines you can see going in here. This is actually something that's very characteristic of this particular planetary nebula. Let's drop that down a little. See these? You can see these radial lines in here moving toward the center. So this white dwarf in here being so hot is actually quite able to energize the gas that it's expelled and ionize it. And again, that's this little guy right here, right there, guy inside that box. That is the source that makes all of this glow. Yet the thing that's funny is that's a star that's no longer doing any fusion. It's just the hot core left over in star death, which is really interesting. James Hyatt's with us. How you doing, James? Good to see you. Daisy and Zoe, how are you guys? Nice to see you. But you can see the striations here, these lines. You can see this going toward the core. This is one location where if you were located here, you would not survive. You would literally be torn apart by this radiation. It's really, really bad. Earth is a dangerous place in the universe. Saiskilski, I'm guessing that's what okay. I'll just call you a skill. Skillski says. Now this red is hydrogen gas that's been ionized, as is this. Okay. The green, that's ionized oxygen, doubly ionized oxygen. And that doubly ionized oxygen has made this green glow here. So it's nice to see you guys here. Thanks for coming out tonight. As I mentioned, I just got back tonight from Arizona, and I couldn't wait to get back to here because I wanted to actually go live with you guys and show you some cool stuff. And sure enough, we're getting it. Let's see if we can go in even more now. Look at that. This is really something. Let's kick it up a notch. All right. Look at the detail in there. This is beautiful. Now this is stuff, as I said, that was not visible to us with the last camera, because the last camera the last camera was actually not tuned for this focal length that we're using. Not as good as this one is. So this is looking pretty. I'm gonna zoom back out now. Yeah. So this is a kind of a proof of concept stream to show you guys what's going on. All good so far. This is excellent. I'm going to tell you, I actually went to the new Sky Tour live stream site number 3. Site 1 is here in Connecticut. Site 2 is where we're looking at now. And Site 3 is a couple miles westward on that desert road at another location. Again, some very nice friends are allowing us to put another building there. And this one's going to be a little bit different. I had talked about using linear actuators, but after looking at the size of the building and the fact that we're going to include different sets of telescopes in there now, it's going to be a building with an arched roof, and it's going to slide off, and the linear actuator will take that half circle end wall down to the horizontal and then put it back up, and then the roof will come back on. So it'll be like this. So the roof will go off, that wall will go down, and now we have 3 sides. 4 actually, because the side to the east, there's some trees in that distance, and the roof will disappear into the trees actually in terms of visibility. But it's gorgeous. It allows us and affords us the ability to look right to the horizon, which no astronomer in his right mind would do. However, if we wanted to look at Omega Centauri, we would do that. And that's exactly what we'll do. And there are some things down that low that were just invisible to us because of our walls of our building. So this is a fabulous opportunity for us. And it's going to be big enough to put more than one telescope in there. And guess what? We're thinking of a solar telescope. So we can stream during the day and at night. And I will never get any sleep. And it's going to be a hydrogen alpha telescope, we think, that'll allow us to see the prominences coming off the sun. And that would actually be a fairly simple telescope. It doesn't have to be very complicated. Because the sun is so bright, right? So we just need one that can show us the resolution that we need. And then we'll be able to take it a step further and do great photography of these prominences, do solar events where Mercury passes in front of the sun, or even the International Space Station, and catch it. You know, in the same way we captured, the meteor striking the moon. So it's all good. It's all good. All right. So the new site then is going to have a building on it that's maybe 8 by 10 feet in size, and it's going to be a small pad with these 2 telescopes on it. Might be a little bit larger, but the nice thing is with the arched roof, we're going to, as soon as the roof comes off, it means that the telescope walls are going to be down well below the telescope, so we'll automatically have a view of the horizon immediately. It's going to expose the telescopes. I wanted to use I wanted to see what would happen if we could do this with an arched roof, and I think that's the best approach. I really do. It is the best approach. So, that said, we'll move on here in just a bit. And the Helix is a planetary nebula. And that it gets its name from the fact that it looks like a planet in a small telescope. And that's the idea. That's why people named it that. So here we go. There it is. You got to see me type it out. Yee. Okay, so this is really stunning. And now, if you notice, like I said, we go back to our FWHM. You see that all of our exposures were good. Hey, Izabela. Look who's here. It's Izabela. Good morning, Izabela, over in Bulgaria. By the way, show some love to her. She has been doing some amazing videos and shorts for us. Truly professional stuff. And I just want to publicly acknowledge that and say that that we are very lucky to have her with us. Thank you very much. Yeah, we missed Izabela. Okay, so I'll say this one more time. And that's now done. We're going to save it exactly as seen. So this image now, as you see it right here, is going to go up and be on our server just for you to take down anytime you like. Hello, Ralph Wooden. How are you? I saw you came here a little while ago. Okay, so at this point, we are done with this guy. And as I said, now when we go back to our 1 second, normally we have that green screen. But we're not going to do green anymore because we're actually we're doing something a little bit different. We're actually doing this in real-time colors. And I'm just going to bring us down to a normal size frame here. Okay. All right. And so this gives us the opportunity now. We don't need that anymore. This gives us the opportunity to see things normally. And we're actually subtracting a dark frame, master dark frame, with every shot as well. So we get rid of things like the noise of the sensor and the vignetting of the sensor, all these amazing changes. And we're also getting only the best focused images. Okay, so let's go to our planetarium program. And you'll see where we are. You'll see that we're literally down near the horizon. But why don't we check out Saturn while we're here? There we go. We're heading up to Saturn now. Saturn is going to be bright. There it is. And we'll have to tailor our settings to allow us to get the best out of Saturn as possible. Okay. And right away, let's go back to let's go back to here and zoom in on Saturn a little bit. And I'll tell you why. Because I want to see where the moons are. So if we come in now, okay. So there's Saturn. And we have Rhea and Enceladus to the left. And we have Tethys, Dione, and Titan is off to the right here. Okay. And you're going to see Titan. And you may see Rhea, but maybe not Enceladus. We got to see. So we're gonna have to zoom in for this. Okay, but first, what we're gonna do is drop this exposure down. Let's go to 50 milliseconds, which is just a fraction. Okay, there we are, and let's zoom in now and see. That's Titan. You can see right there. All right. We'll take a regular picture too. There's a lot of noise in here. Our sensor is running at minus 19.5 Celsius. Our target was minus 20. And the cooler is running at 57% of power, which is actually quite good. So now you'll say, well, that looks pretty ugly, Mark. I know it sure does. Let's drop down though. Let's get rid of this and this histogram here, the one on the right there. There we go. Well, look. Well, now Saturn looks like a Saturn. And if we pull up the brightness just a little bit, we'll be able to catch Titan. There it is. We're pulling in Titan over here. Okay. And you'll notice Titan is actually going to be a little orange. But let's do something. Let's drop down. Let's get rid of this actually entirely. If we want to expose so we can see the planet, then we have to necessarily not see the moons. So it's kind of low on the horizon a little bit, but we can try and see if we can capture any detail. Remember, this is a wide field telescope. Well, you can see the rings. We can see the rings. Yeah. The next telescope is actually going to be a really long focal length, meaning we can magnify quite a lot. So we'll be able to see this in intricate detail. So not bad. Not bad for just a quick pick of Saturn. Well, let's actually take an image. Let's do let's try 3 seconds first. And go back to our live stack here. Get rid of that. Look at that, huh? That's the previous view. That's not bad. Okay, we'll clear that now. Okay, and the first one was 9.5, so it's not actually able to get Saturn yet. The wind is obviously kicking up out there, preventing it. I mean, if you want to see what it can do, we can just bring this up to a very high value and capture an image. Okay. So there's an image. Okay. So let's go over here and drop it down. Notice how orange Titan is. All right. Okay. let's go back to this. And so we have Titan out here, and then we can see here we have another one here, and we have two more here. Let's go back and see what those are. Okay, we're probably looking at Mimas or this one. Oh no, it's these two, Tethys and Dione. Okay, that's what we've got there. And Tethys and Dione are pretty close, and Enceladus is buried in the glare here, so we're not going to be able to see it very easily. We'd have to do a shorter exposure. So that's a little bit of an issue. Cool. Really cool. All right. And there's Titan, and there's Titan. So the stack is showing these, and then we have Iapetus out here, which we saw, Tethys, Dione, Titan, and Iapetus. So we have Tethys and Dione, Titan, and Iapetus. And there's one more, but is that? Oh yeah, that's this guy right here. Okay. And this is probably a star. Yeah, it's a star. Okay, so and then in the glow here, we've got these two here. Let's try and drop down the glow a little bit, and let's try and do this again and see what we get. See if we can capture all of them. Let's see. Okay, let's go up higher then. Guarantee that we get an image. Okay. We're getting a burst of wind out there, obviously. That's all right. If I turn it off, let's see what we get. Yeah, you can there we go. Now we got them. You can see that right there. So, looking at Saturn's moons, we see Enceladus and we see Rhea. Now, what's interesting about Enceladus, that tiny little dot right there. Okay. Enceladus is a place where we think life might have taken hold. It's this little tiny guy right there. All right. And so Enceladus has an icy mantle, an icy top, icy surface, and beneath its surface, it's got an ocean. Now, Enceladus is only 300 miles across. It's a tiny moon, nowhere near as big as Europa, which is 1,920 miles in diameter. But like Europa, it has a active interior and water. We see out of this tiny moon right there, we actually see geysers of water coming out from the South Pole. And when the Saturn probes looked, like Cassini looked at Enceladus, it saw that it had rippling structures of heated areas underneath. And those rippling structures of heated area were akin to what we see here on our Earth with the sulfide chimneys and those hydrothermal vents in the deep ocean. And so it seemed as if we were seeing a similar thing. That's pretty cool, considering that would mean that this process is not just limited to Earth. It's amazing. Here we go. That's even better. So there's Titan, there's Iapetus, there's Tethys and Rhea, and there is Enceladus, that little tiny dot, and then we have what did I forget that already? Europa and Rhea. Okay, so it was Tethys and Dione, and then Rhea. No wonder I forgot. So it's Tethys and Dione, and then Enceladus and Rhea. Here we go. How pretty. So there's the Saturn system, the moons that we can see. Pretty cool. All right, let's take this down to 7.96 will do for now. Okay, so let's get rid of the stack here, and let's get out of this. Let's go back to a level where we can see this now in our, there we go, our realistic view. Okay, let's go back now and find something new. Izabela, thank you for putting those out there. Izabela has been very kind to help us see all these amazing things. We're going to go right to another object that I'd like you to see. And we're going to do it. It's quite a hike. Did you guys want to see the Andromeda Galaxy tonight? If you do, I will show it to you. Ralph Wooden asks, is that due to tidal friction / warming? Yes, Ralph. It's due to two things. It's due to the heat of original formation, which will allow for what's called differentiation, where the radioactive heavier materials fall toward the center, and then it will allow for this kneading, Kneading, kneading like bread of the entire planet by not just Saturn, but Saturn's pull and Dione's pull and Tethys and the other moons traveling around Saturn that are also tugging on poor little Enceladus and causing it to just do this kind of stuff. So it's pretty cool. Vince Giglio, haven't said hi to, I'm sorry. Hello there. Okay, let's see if we can grab Andromeda. Watch the telescope right there. You'll see it take a hike. It's hiking. All right. Let's see if we get close. There it is. The Andromeda Galaxy. All right, now, the Andromeda Galaxy obviously is too large for our new camera. It was just a little bit too large for the old camera, which had a larger field. The field of view now is 1.5 degrees by half a degree. And if we go and look at our object here, we get our field of view indicator, that square rectangle. That is our view indicator. We zoom in, and it's going to be upside down, but it's 1.1 degree, 29 minutes, so 1.5 degrees by 59.62, so by 1 minute, 1 degree. So it's 1.5 by 1 degrees in size. So that's actually really impressive. And it's more tuned, way more tuned to our telescope, that camera, than the previous one. So that actually is a very, very helpful thing. So we're going to drop this down low. And you'll say, why? Andromeda's up there. But an Andromeda galaxy is way bigger than this image can show. So we're going to actually do this. We're going to move over a little bit. Right about here. And then move this up. Okay. There we go. So now this is all going to have galaxy in it. We just don't see it yet. Now I'm going to do a 20-second shot here. Bring up our stack. And I'm going to we're going to stay at 7.96 here and just see if we can get ourselves one to come in. Good. Look at that. So we get almost immediately better results now that we're subtracting a dark frame. We're getting much better processed images right up front in the raw format. Hello, Mr. Django. Okay, we're going to go for the beautiful Andromeda galaxy. Okay, so let's do this. Let's, I have to get rid of this. I had a double histogram running, my apologies. Oh, look at that. And now we're going to do that. Look at that. What's really beautiful about the Andromeda galaxy is, first of all, when you look at it on the drive, look at it, flip it the other way, flip it this way, and look at it across the top. This is the near side to us, and this is the far side. So it looks like we're kind of looking at it kind of from an upside down perspective now, from like the bottom. If you think of it that way, you can see it. But if you see it the other way, and some of you are turning your head now, you can undoubtedly see what I'm talking about. You can see that three-dimensional nature almost a little better. Okay, so here is the next thing to consider. And that is, here's what I'm going to do, first of all. Okay. We're going to do this right here. Notice our curves are slammed against this side here. That's because we don't have any areas that are excessively lit from noise. The dark frame is removing a lot of it. James Dugan, welcome to you from Australia. I'm glad to hear you are here with us tonight. Lynn Beats is with us. That is Kyle. How are you, Kyle? What's going on? He says, how do the darks and biases work with the configuration you have on the Mead? I'm curious on how you're able to achieve this. We're actually doing it. You see this program here, Kyle? This is called SharpCap, and it allows us to specify alignment parameters, stacking parameters. We can do enhancement. Right now we're enhanced. It allows us to look at guiding, and it also allows us to use that full width half maximum number. Our upper limit is 7.96, and all of our Andromeda shots are coming in at 5.9, 5.8. So in other words, the size of the stellar image is exceptionally small. It's really, really good. So we're doing this all from SharpCap because it works very well. Yeah, see, this is what you like to see. So let's go back to our histogram now, and let's see if we can do a little processing here. Look at that. Oh, wow. This is the top of our curve. All right, and let me see if this makes a difference. Yeah. So usually we process just to the left of the top of the curve. All right, so we'll go there. But I want to show you some things. This is cool. Let's do this. Let's actually move this out of the way, and let's put us into a full screen here. That's cool. So this is literally a portion of the Andromeda galaxy. It's about 2.4 million light years away. So everything you see in that view, other than the stars you see, are 2.4 million years in the past. And so when we look at the galaxy, these stars that you see here, these are all up here in the foreground in our galaxy. And that galaxy is way out there, 2 million light years away beyond them. This image will be available up there for you. And because we're using our full width half maximum, we're going to definitely only be bringing in the best imagery. All right, and I'm going to turn off the enhancement for a moment and try to view it without it for a minute. So, what do you notice when you look at a galaxy like this? It's a spiral galaxy. Here are the spiral arms. Okay, you see this dark dust. Well, we see that in our galaxy too.
Just passed through meridian.
Okay, we just had a meridian pass through with a telescope. So what it means is that the blue that you see there, along with these dark stuff, this dark material, this is the refuse, the debris left from countless billions of supernovae. And that material is made mostly of carbon atoms, and silicon atoms, and additional ices that form on the surface because you get compounds in the dark of space and the cold of space. So there's methanol, there's carbon dioxide ice, water ice, there's ammonia ices, and methane ices. You've got all kinds of hydrocarbons that are attaching to these atoms of carbon, forming an interstellar dust grain. And those grains are really small, but there are many of them. So together they make a cloud of dark dust. And you'll also notice that this galaxy is punctuated by these orangey yellow stars and a really prominent disk of blue. Well, blue stars are hot and young, all right? And so hot young stars are, sorry, I've been flying all day. Hot young stars are actually stars that are formed from gravitational contraction of dust clouds of lots and lots of gas and dust. Well, a star doesn't house dust per se, except in its outer atmosphere and only if it's very large. But what we see with a galaxy like this is that these hot young stars were formed in stellar nurseries. And you can see stellar nurseries in here. Let's try to make the stellar nurseries a little more visible. To do that, I'm going to drag this down just a little. There we go. Let's wait for that to sharpen. Okay. So you'll see up here, there is a little reddish cloud. And then as we move down through, I've got two monitors, guys, so that's why, I'm not sorry, not two monitors, but a big curved monitor. So I'm looking on both. All right. And so now you look down in here, you'll see that there's red areas in here as well. These red areas are stellar nurseries. And we see a lot of stellar nurseries. There's one right there. Okay, let's see what else is in here. Let's pop the entire image up brighter. Okay. Look at that. And now you actually can see, and there's a little more noise, yes, but maybe we can adjust that a little bit. Okay. Yeah, that's just something else. So, let's see. How many frames did we have in here? I think every one of them was a good one. I don't think we lost any. No, all of our frames in the stack are good. Yeehaw. All right. And there's 27 shots. I'm going to go to 30. Then we'll look at the other side of the galaxy. So let's actually bring this back docked over here, and let's pull the telescope back. All right, there we go. Hey, Hunter, how you doing? I'm all right, thank you. My son just got home from work. Thank you. It was excellent. I just got back, a couple hours ago. Not even a couple hours. Yeah. I was working on the observatory and I was teaching astronomy in the desert. It went very well. It was very hot. And of course we had someone fall in the cholla, as they always do, and they had all these spines sticking out of it. It was a horror show. We had to use pliers to pull them out. Yeah. Anyway. Huh? Oh, he had probably 30 spikes in him. Yeah. I know, it's really bad. Well, I'll talk to you in a bit. I'm just streaming right now. No worries. Good to see you, man. Alright, thank you. He works for one of the biggest television stations in the state, and he just got home. It's 11 o'clock. It's midnight right now. For me, it's 9 o'clock, 10 o'clock, because Arizona is 3 hours behind when I went out there, and then 2 hours behind while I was there. You notice, though? Every star, look at that. Look at that. They're all perfectly round. Yeah. Having this automatic process to get rid of bad frames is the best thing that we could have done. And adding the master dark frame removal makes every image a much better image right from the start. And then we process that for you guys. Oh, yeah. Look at that. Man, that's beautiful. Michael Hedrick. Hey, good to see you, man. Yeah, Kyle, who's Lynn Beats in there. You can go up to our server here at skytourlive.org, and you can download these raw ping files. You can also download the FITS file as well and do your processing on the FITS file if you want to. The FITS is our... Let me just save it once I rename this here. This will be M31 South. Okay, the south side. And this is 36 images. We're going to save it. And save it exactly as seen, babies. All right. Okay. Now, let's take advantage of this good seeing tonight, right now. And let's actually go look at the north side of this galaxy. And let's go back into our enhanced view. Drop it down. Okay, we're going to drop that nucleus way down. Okay, and now we'll have this galaxy in the view. And I'm going to have to split the difference. I don't want to lose that galaxy in the view. Right there, that little one. So I'm going to move this over to the edge, but not out of view. So we'll lose a little the edge of the galaxy here, but we're going to just split the difference. Michael Hedrick has a real technical question. All right. All right, let's see what's going on here. Make sure this is good. Excellent. Michael Hedrick says, are astronomers able to detect ancient supernovae as their light travels across distant galaxies when we measure distances in galaxies with... let me read this again. Are astronomers able to detect ancient supernovae as their light travels across distant galaxies? Can we measure distance and galaxy width this way? That's an interesting idea. But we can see if there's a medium through which the light can pass, we might be able to see it. Supernova 1987A, which occurred, I believe, in one of the Magellanic Clouds in 1987, we saw a light echo traveling through the clouds. But keep in mind that, unfortunately, one of the problems we have is that light attenuates by the square of the distance. So when it goes 4 times away, 4 times the distance to you, it's 16 times fainter. So a light echo is going to fade dramatically as it heads out from a supernova source. So it would be interesting, though, to see what that actually looks like. Okay, we can actually move this over just a little bit more. I don't want to get too close to the edge, but let's move it over a little. And we'll take a photograph again. Here we go. So, although it looks like it's off the edge, it's not. You can see that it's right there. And this is all up here. All right, that's perfect placement. And now what we'll do is we'll do another 20-second photo. And do this, get rid of that. Go into our stack. You'll see the last one. It's obviously a little under processed. There you go. Beautiful. Okay, and now we're going to see above it up here. All right, so we're going to see the first image and see how nice this looks and smooth. Okay, well, now we see this, okay, because it's the first image of many to come. So we see the upper part of the galaxy, and yes, Izabela's going to probably put them together. All right, and so you'll notice this galaxy, as this sharpens up, this galaxy actually has quite a bit of detail in it that we've never seen before. Never seen it, but it really has some nice detail. And you already can see it has a dark cloud in it. Really neat. Yes, sir. And let's color correct. Well, Michael, when it comes to measuring the distance across the galaxy, you'd have to be able to pick up that light echo traveling all the way across the galaxy. And the material that's coming out is actual matter. It's not light energy. So the light energy would have to be detectable across the galaxy. So unless it has something to collide with, and unless it has something to reflect off of or pass through that is a detectable echo, then we'll lose it. And so could that theoretically work? Absolutely. But is it practical? No, unfortunately it's not the best approach for doing this type of analysis, but still, it isn't bad. It's a good thinking, by the way. Kyle Lynch says, how are we able to detect light echoes? I'm curious. Well, with the telescopes, when we take pictures of these images, of these objects, these supernovae, we can see a light wave. We can see like a light front. And then you look at it again a year later, and you see that it's moved, maybe even a few months later. Cosmic Ray says, wow, no blobs tonight. What did you do? Well, I was showing folks before, Ray. I did this. I added a full width half maximum filter so that what that means is if the star image is above a certain size, I do not accept it in the stack. And so it's eliminated from the stack. It's sort of an auto culling process. So notice these are all in the 5.7, 5.8, 5.7. So that's ideal. Yeah. And if you notice now, this galaxy, in fact, all of these images are showing way more detail than they've been able to because we're rejecting the bad imagery. And I apologize for my yawns, but I have been flying all day long. And as Ray says, my arms are tired. I've never heard that joke before. This is fantastic. So, you notice up here, look at these beautiful star clouds up here. Also, look right here. You see that? You know what that is? That's a stellar nursery complex. You can see the stars in here that are in the clouds of hydrogen that are red and forming new stars in here. It's really, really pretty. Now, what's really interesting is this galaxy here. This is a companion galaxy known as Messier 110. And Messier 110 is a companion to Andromeda, like the one down below it is, Messier 32. But Messier 110 is an elliptical galaxy. And ellipticals tend to be devoid of, have no gas and dust. So this is an oddball in a way because you can actually see a dust cloud in here circling this galaxy's core. So this has, and there's some gas in here as well. It's very strange. This elliptical galaxy does not follow the standard pattern. I would love to get a Hubble Space Telescope view of just this galaxy, because it would be something else. But look at all these blue stars, this hot blue regions. Here's more stellar nurseries here. You can see them very clearly. Let's go down here a little. Really nice. We also see supernova remnants in here, greenish. I'm going to try to coax out a little bit more data by just cutting the noise level just a little. Kyle says, what makes this galaxy different from Andromeda? Well, first of all, when you look at Andromeda, all right, it has massive amounts of dust, right? And it has spiral arms. It has hot blue star-forming regions. These hot blue stars in these clusters, these are called OB associations, O and B type stars. Very, very hot, very, very young. This does not really have that at all. This is like an elliptical galaxy. It's sort of an elongated sphere of stars, basically. It's been elongated. And they typically don't have dust and gas in them. But here we see this one does. It doesn't have any spiral arm structure that we can see. It doesn't have any hot young star formation that we can see. But it does have a little bit of dust. That little bit of dust makes this unique amongst the elliptical galaxies. Anthony DeSanto, how you doing? Alex Lopez, how are you? Anthony DeSanto asks about any field of view that has a multitude of galaxies. Oh, yes. When we get to the Virgo cluster, which we don't do tonight because we can't see it, it's not up, we can see many galaxies in one shot. Many, many galaxies. Just incredible. Really, really nice. I'm going to let this percolate for a few minutes. Alex Lopez says, how come we can find the darkest planet in the universe, aka test 2b, test object of interest? We can't find a planet that they say is roaming the solar system. That's actually an interesting question. First of all, TESS was looking for transits. So it was looking for planets that were passing between its bright star and you. Okay, so if my face was a star, a planet passes in front of the star, it's taking some of the light from this star and making it get dim. So if the planet's passing by, all right, this part of the planet is causing a little bit of dimming of the star's light. All right, in our outer solar system, we don't have that massive contrast enhancement to locate a dark planet. All right. So the TESS, transiting exoplanet survey satellite, was really quite the workhorse when it came to this, because it had like a 96 by 25 field of view, looking for all of these amazing transits. This is really shaping up beautifully. And the stars are beautiful. My flight number on the way home was 1017, flight 1017, which happens to be my birthday, October 17th, which I thought was kind of clever. Really neat. Okay, so let's see. Yeah, okay. Kyle's doing a processing, he says, on the helix. That's excellent. Izabela says the stars are perfect. I know, right? It's much better. Oh, it's much better. Ralph Wooden answers Anthony DeSanto about galaxy fields. He says that there are tons. Look up Markarian's chain. That is correct. Markarian's chain, again, toward the Virgo side of the world, is really an amazing location. The Virgo cluster is a supercluster of galaxies, headed up by Measure 87, the Virgo giant elliptical, which doesn't seem to have any dust, but has jets of highly energized material streaming out of its north and south polar region, and that is due to a supermassive black hole at the center that our telescope, called the New Horizon telescope, actually imaged. And we had the first ever in human history image of a black hole, thanks to the New Horizon telescope. The consultant on that movie, which was Interstellar, the movie Interstellar was the consultant was Kip Thorne. And I might have mentioned this to you before. I think I have. Kip Thorne is an astrophysicist, and I sat with him for about 3 hours and talked about black holes one day. And he basically discussed how black holes operated and so forth, and then he proceeded to talk about the design, how it would actually look, and he ended up years later using that in Interstellar, and then we saw the first images of a black hole, and guess what? They matched Kip Thorne's prediction exactly. So that's pretty cool. In fact, a lot of people thought it was faked because of that, but it wasn't. It was actually just good science, and science vindicated, actually. I'll read some chat here, see what's going on. Hey, Christopher Thompson. He's asking about planets. Just a little while ago, we checked out Saturn and identified all of its moons that we could see. I'm sorry that you missed that. We can probably check out Jupiter for you. Again, this is a wide field scope, but we can check out Jupiter, biggest planet in the solar system. So I think that'll look pretty good for us tonight. Let's check it out. All right, we have the same, just about the same amount. Here we're gonna do this as measure 31 north. Wow, see, we're never gonna have a bad image train again, ever. Okay, save. So we saved the FITS file. We're gonna save the ping file exactly as seen. There we go. And those files are now up at skytourlive.org. You can go up there and you scroll down to the next dark gray block and it says take me to cool pictures, and it takes you to our live server where you can go and see this picture that I just took moments from now. And if you're interested, with Christmas coming, you might want to think about this. If you're interested in getting some themed gifts for your friends, go to our Sky Tour shop, and you can get mugs, you can get pillows, you can get blankets, you can get shoes with some astronomical objects on them, and we have a lot more products coming, so it's really cool. Anyway, but Christopher, what I'm gonna do is, now that we're done with this, I will go and I'll save this one more time. I will go and bring up Jupiter, because Jupiter should be visible right now. Okay. But look how beautiful this came out. Again, these hot blue regions of beautiful star formation. Look at this nebula right here. You know, that's really, really obvious. Stands out like a sore thumb. Here's another one up here. And when processed, they are even more obvious. And this one, the gas and dust are now quite well defined. All right. Okay. So that's pretty cool. So now we'll head off to the next item for bids here on The Price is Right. Okay. So we're already zoomed out. Let's go back now. We're in the same region of the sky. Waiting. Here we go. And let's go zoom out a little bit. Find Jupiter, which is going to be over here. We also have the Pleiades are up, and I think they'll be visible right in a bit, but I'm not sure. But let's check out Jupiter. All right, so we'll go here. And we're going to check it out. All right. Excellent. Okay. So, we'll go here, and let's now zoom in and check out where the moons are. Okay. Here we have Io. We have Ganymede, Europa, and Callisto. Now, the thing to understand about Jupiter's moons is that they're in a circle around Jupiter. So, at any one time, Io, which is the closest one to Jupiter, may not look like it's the closest planet to Jupiter, because Europa going around will pass around Jupiter, all right? And so at some point you might see Io here and Europa here. It doesn't mean Europa is closer to Jupiter. It means that in its circular orbit, it just happens to be along the line of sight that makes it look like it's there. Okay, so let's get rid of our things here, and let's say go here. Okay, so let's do this. Go here. Do this, and back out so you can see the field of view we're talking about. Okay, notice it's upside down because, well, not right now because we're back to this side, but it's 1.5 degrees by 1 degree in size, as I said. So let's go there now and check it out. And this is for Chris Thompson by request. You can see the telescope moving up there. And when Jupiter shows up, it's going to be exceedingly bright. It's the brightest object in the sky besides, yeah, look at it, besides Venus. And of course the sun. All right. So first things first, we're going to get rid of that, and there's all of our moons. These are the Galilean moons. All right, so let's bring this down. Okay, we'll bring it down, and then we'll go toward the west a little bit. Center it up. Okay. All right, so if there's Jupiter, we now have Io, Ganymede, Europa, and Callisto. Callisto? Where's Callisto? Out there? Let me get it again. Callisto. All right, so we zoom in here. So we have, let me make sure I got that right. Yeah, we have Io. We have Ganymede, then Europa, and Callisto. Okay. So what's interesting is, if this is Io, when we take a photo of it, you're going to see that Io has a little orange tint to it because its surface is covered with sulfur. And so it's a yellowish orange color. So, all right. First of all, let's see what we can get out of this. I should probably reduce the gain, which will reduce the noise. So let's go down to 0 gain. All right, and then let's go to a smaller exposure. Let's go to the wrong one. All right, we'll do 100 milliseconds, so a tenth. Okay, so that's 100 milliseconds. Drop that down a little more. We'll zoom in. This is a live view, by the way, so let's see what we got. There we go. We got some bands on Jupiter. Look at that. Not bad for a wide field system. So we have the main cloud bands on Jupiter right there. That's pretty cool. Let's see if we can help that along. Live stack that. We'll clear this. I wonder if we're going to get them. Let's turn it off for now. Okay. Temporarily. Okay, so now what I'm going to do is do this and bring this up to the... Well, actually, I want to do this. And there we go. As you can see, Jupiter is very bright. So we're going to drop that down and then drop the second one down. All right. Let's go and increase this exposure just a little bit. And try and coax a little bit more. Mr. Django, thank you for dropping by. Great to see you. Oh, I've got to turn this off for now. Well, as you can see, we can coax a little extra data out of that. The live view is better, I think. There you are. Interesting. Neat, neat, neat. Okay, so there's Jupiter. And if we actually do a little bit more coaxing, we can see Io, Ganymede, Europa, and Callisto, the Galilean satellites. Pretty interesting. And increase the gain to 200 again. That's going to be just a little too much for us, but you can see them better. All right, so there's Jupiter. That was for you, Chris Thompson, by request. And what we'll do is we will now move along to the Pleiades. If we could get to the Pleiades, I think those are really cool. If you look up on skytourlive.org, you'll find a most interesting photo of the Pleiades I took the other night. Okay, here we go. Let's see if we're going to get to it. All right, let's go to our 1 second here. Okay. So we are close now. And we just have to move up a little bit. Here we go. There's over there's well over 100 stars in the Pleiades. It's not just what you see here. The Pleiades star cluster is only 400 light years away, but it's really got a ton of stars in it. Many of them are hot and young. The brightest ones you see here are all B type stars, so not O stars, but B stars. The next brightness level. Okay. Well, this is Pleione, Alcyone, Merope, Tegeta, and I don't want to forget one. Okay, okay. Let's just zoom in here. Yeah. Yep. So there are a number. See that dust, that beautiful dust cloud there? That dust cloud is something that you just don't see here, is it? Right? You don't see it. These are the main primary stars, right? Well, we're guiding now. You can see by our numbers changing over here. So what I'll do is I'm going to take a 25-second shot. And let's go into our stack. And let's do what we've done before. On our filter, we're going to filter and see if this will with the thing facing up like that on a windy night. I'm not sure we'll get under 7.96, so I may have to increase it, but we'll give it a shot. 10, wow. Yeah, that's quite high. I could shorten the exposure, and that might do better with a windy night. This one doesn't come in. Okay, it's in 10 as well. I will shorten the exposure to 20 seconds. And I will increase this to it went to milliseconds. My mistake. All right. 20,000. Okay. All right, let's go into our Instagram. Let's see if this is going to work. And windy nights are not the best, you know. But I just wanted to bring this out for you guys to show it to you. I'm going to clear this because they did not come in. Yeah, this thing is a gigantic flag in the wind. You can't really see it, but I can see stuff, you know, dust and things flying through here. Tell you what, just so you can see something, I'm going to turn it off. So you will get an image. Hey there, Trisha Ferrara. How are you? Christopher asks, are there known planets around any of these stars? No, not that we have seen yet. Part of the reason for that has to do with the fact that these stars are very hot, very young stars. And very hot young stars tend to have a lot of ultraviolet radiation that they send out. So it's a little difficult for them to have planets, because the planets would not be able to survive. Maybe not even form at all. So there you go. There's the Pleiades showing up. Let's zoom out a little bit. Oh, you're seeing halos around each of these stars. That's because it's a fast optical system. So this star cluster is about 400 light years away or so, and what's happening is it's passing through a dust cloud, and these blue clouds of dust you see here are actually clouds of dust that are not associated with the Pleiades. All right, they are, the Pleiades are just passing through them. They might say, well, how do you know that? The way we know that is because a velocity study of the clouds of dust shows they're going one direction and the stars are going another. They're just happening to pass through each other for a period of time. Wow. This right here is really cool. That little tongue of dust being illuminated. Now this nebula around here, these nebulae are very interesting because what they do is they show us something fascinating. They show us that the dust that we see around the Pleiades is made of this very, very small carbon atom dust and silicon atom dust. And what's going on is that this dust does what dust will do, and it is going to scatter high frequency light. And so when you get the spectrum of a star, which is red, orange, yellow, green, blue, indigo, and violet, all those colors, when you get that coming into the dust, the blue light gets absorbed right away and then sent out in many different directions. So blue light comes in, it goes choom, bing, it comes in again, bing, choom, gets shot off in different directions. So every direction you look at, in every direction you look, you will see blue light. And it's glowing blue for the same reason our sky is blue, right? So the sky scatters the high frequency or blue light. Blue light is short wavelength. Long wavelength light is red light. So red and blue. Blue is short. Red is long. And blue light, short wavelength light, is very easy to scatter. And so that's what happens. Very interesting. Well, for this particular exposure, I can actually probably do that, because that shows reasonably round stars. So we could get all of our exposures inside the realm here. Thanks, Kyle. I'll check out your processing later on. This is really nice. We can get rid of these halos around the stars now pretty easily. That's something that we do. I showed Izabela a way to do it as well. We tune each image to whatever value is best for showing the stars as small as object as possible. Hey Fantasy, how's it going? Oh, thanks, man. I'm glad you liked the Andromeda galaxy. Well, you're typing in the group chat, Lynn Beats. But if you mean in the SkyTour live stream group, yes, there is a group up there. There's still a group up there. See, look at the detail. You can see a tremendous amount of detail in this dust. And we'll see even more. So what we're going to do is we're going to copy this. And save it. This is 16 frames with 5 ignored. Yeah. Fantasy says, pretty cool. I see it out of my window and here you are taking a live picture of it right now, basically. Yep. Pretty cool. Okay. Well, guys, I don't want to be a downer here and cut this short, but I have been flying in the air. Because you don't fly underwater. I've been flying all day. So I started my day very early, and I had only just got home a couple hours ago, so I am going to call it tonight for now. I'm really happy you're here, and I just had to share this with you, these new developments, because we can get perfect images from now on. So I'm going to go get some rest, and when I wake up tomorrow, I'm going to go and process some of these images. Izabela will probably beat me to it. That lady is supremely talented, and as I said, show her some love for all the wonderful video shorts she's been doing for us. EM, thanks, man. I'm gonna go conk is right. All right, guys, you have a good evening. I'll say this one more time, and I know I marked one more, D'Antonio. I always like to do one more, but I just don't have it in me tonight. But don't worry about it. It's not gonna... Oh, look at that. Wow. Ugh. Yep. That is just something. Okay. Yeah, that's just something, I'll tell you. Looks good. Really good, Captain. I'm liking that a lot. Scotty, I have to go to the Pleiades. I said, we all want to go to the Pleiades. I know a nice little bar up there. Alright, guys. Well, you have a good night, and we will talk to you, well, when I wake up. So thank you for joining me, and we will talk next time I see you. Good night, everybody. Oh, and I have some pictures, too, that I want to show you as well. So I'll get those ready, too. So good night, everybody. Bye-bye.